Now that we know how the measures of location and spread can be used to describe our data, let's see how we can better visualize them through graphic methods. Let's start with bar graphs. These two bar graphs show the vitamin A consumption of two groups of people, those without any forms of cancer in their bodies and those with cancer. The x-axis show the quantities of vitamin A taken daily in terms of recommended daily allowance, or RDA. The lowest amount shown is less than or equal to 1/2 of the RDA, and the highest amount is greater than twice the RDA, but less than or equal to 5 times of the RDA. The y-axis show the frequency of individuals that belong to the categories defined by the quantities of vitamin A that they take daily. This frequency is expressed in percentage. By just looking at the heights of the bars, what can we say about the two sets of data? More people in the control, or those without cancer, consume greater amounts of vitamin A than what the RDA requires. And a majority of the people with cancer consume lesser amounts of vitamin A than what is required based on the RDA. Here are other steps by which we can construct a bar graph. Take note that each of the bars in the bar graph is separated from one another with a space. This means that they are not contiguous. A special type of bar graph may be seen here in this histogram. Notice the bars are now next to each other without any gaps. Each bar represents a class interval. The boundaries to the left of a class interval is its lower limit, and the ones to the right is its upper limit. The value at the center of the class interval is the class mark. The class mark is the mean or average of the values within the class interval. By the looks of this histogram, we can see that the mode is found in the third class interval, and that the shape of the histogram seems to trail longer to the right, forming a tail. We can therefore say that this histogram is skewed to the right, or skewed positively. We may simply use a line connecting the class marks from the histogram. The result is this frequency polygon. A quite remarkable way of both showing the shape of a data set and allowing an audience to see the distinct data points is by the use of a stem and leaf plot. Here's data, a data set of 100 live birth weights in ounces from a certain hospital. Here's how a stem and leaf plot will look like. The stem is a vertical line of numbers along the left side of the plot. The leaves are the numbers building to the right of the stem. Notice that the numbers 4 and 7 on the stem don't have any leaves to their right side. This means that there are no data points in the data set that start with the numbers 4 or 7. The leftmost column of numbers is the frequency. We start counting both from the top and from the bottom. So both the top and bottom frequencies are 1. Then we slowly move forward towards the center. When we reach a point where adding the additional frequency results to a frequency greater than 50% of the total number of data points, we stop. So as you can see here, we have a frequency of 1 because of this, 32. And here we have a frequency of 2 because we add the first one to this, and that's now 2. And here we have a frequency of 5 because we now add the 2 before this, plus the 3. And so we slowly add, building up towards the center until we reach this number 45. But the problem is if we add the 10 more or the 11 more to the 45, that's going to be greater than 50, which is 50% of the 100 data points. So to solve that problem, instead, we just write the absolute number of data points in this particular leaf. So in this case, 17 is written within parentheses. Take note that adding all the data points in the stem and leaf plot has not sacrificed the graphic representation of our data set. Here we see a very similar looking graph as that of a histogram. Are the data points skewed to the left or to the right? Finally, we have the box and whisker plot. In this type of graph, the 75th and 25th percentiles are used as upper and lower boundaries, respectively, of a box. This is so because a majority of the data points are found within these two quantiles. The median, which is within the box, is marked by a line. The mean may also be indicated with a plus sign. The whiskers or tapering tails of the box plot represent other data points that are not part of the majority. The outliers are represented by zeros, positioned as extensions of the whiskers. By the looks of this box plot, you would be able to see that the data points represented here are skewed to the left.